Hello, my name is Rob Reynolds. Welcome to Calculus Section 3.3. Today we get the rules or definition of how to take the derivative the shortcut way so we don't have to use the limit process. So remember in sections 3.1 and 3.2, you need to demonstrate your content knowledge by doing the limit process. The limit of the function of f of x plus h minus f of x all over h. I will be testing you to see if you can do that process and find the derivative, but if they don't ask for the limit process, let's do it the shortcut way, section 3.3, and then throughout the rest of the book. So the first thing you need to know is that the derivative of a constant is 0, and here's a demonstration of that, because remember, the derivative is the slope. So if I have y equals 5, and I graph that line, notice that the slope is 0. And then here's a nice, finally, you're waiting for this definition of the derivative. And so if I ask for the derivative of 5x squared, you'll take, according to this n is this 5, so it's 2 times the 5, which is 10, and then you decrease the exponent by 1, which is just 10x. So I'll come back to this graph. This is a neat way to look at graphing. If I have just the regular function here, here's f of x. We talked real quickly in the last video about if the slope equals 0. If the slope equals 0 on the function, then that creates a 0 on the derivative. So you can see here's the first derivative. So if the function, so what I want to show you here, if the function is this red thing, kind of looks like an x cubed. Well, the derivative of x cubed, now that we have that definition, we don't have to do the limit process, is going to be 3 times this 1 out front, which is 3, and then it decreased the exponent by 1. So it's an x squared function, and sure enough, this guy right here looks like my x squared function. So that's one cheat way to be able to graph derivatives, is just take the derivative of it. Here's the proof of why this definition works. If you're interested in that, read. I'm just going to go through and give you some examples. So the derivative of x to the 9th is going to be 9x to the 8th. Again, I multiplied 9 times the 1 out front and then decrease the exponent by 1. The derivative of x is just 1. Or you could say at 1x to the 0, but that's just 1. And the derivative of 2/8, remember, that's just the derivative. They're trying to fool you here. That's just a constant, so that's going to be 0 using this definition. And here are solutions. So instead of using the limit process, we're saying, okay, we can just take the derivative of this thing. And notice when you're taking the derivative of a constant, this isn't a very helpful rule yet, but it will become much later. We can just pop out that constant. So again, the example that I gave you before, I think I said 5x squared. We could think about it as 5 times the derivative of x squared and then work inside here. The derivative of x squared is just going to be 2x. I don't know why you would want to do it this way, but that's one approach, and we get the same answer. I think it's much faster. If it's not a complicated problem, do not pop out the constant. Just take 2 times the 5, get the 10, and decrease the exponent by 1. But I'm just showing you, we will be using the constant rule. It's very helpful, but not in this case when they're simple. We'll be popping out constants when it gets a little bit more complicated. So again, the book may want to take this negative 7/8 and have you pop it out. I'm not going to encourage you to do that. I don't do it. So I would go ahead and just take 11 times 7. Actually, that's a negative 7. So negative 77x to the 10th, decrease the exponent by 1, and the 8 just drags along. So when you have a radical, it's sometimes helpful to rewrite it as an exponent. So I haven't taken the derivative yet, so let's do so. It's going to be 3/8 times the 1/2 t to the 1/2 minus 1. Well, that's just 3/16 t to the negative 1/2. And the rule of thumb is if they start with radicals, you give your final answer in terms of radical. And this is a negative exponent, so negative exponents reciprocate. go back into the denominator, and I'll write it as a radical, the square root of t. So remember, this is really 3/16 times 1 over the square root of t, and of course, it just simplifies to this. So the constant rule is not very helpful. I'm going to skip it for now, but it will be helpful later when they become a little bit more complicated. Here's how the book chose to pop out that constant first. I think that's more work. Also, I'm not going to spend time deriving or giving you a proof of why we can take the derivative of a sum. We can just take the derivative of the first plus the derivative of the second. But if you're interested in wondering why these things work the way that they do, here's a slide that explains what gives us the power or the right to think about taking the derivative of this 2w cubed, which is 6w squared, and then take the derivative of this guy, which is 18w, minus 6 plus 0, because the derivative of the constant is just 0. So again, I'm invoking this rule, but I'm not going to write it out. I'm just going to kind of do this in my head. I hope you followed along, but that's the answer that they're looking for, and we just skipped this big, long process. I would not expect to see any of that on a quiz or a test. Don't create work, but I do want to see work, but I don't think there's any work to be shown here. So next we're going to look at how to find the derivative of e to the x. Now remember, e is a number just like pi. It's equivalent to around 2.71828. It's an irrational number that goes on forever and ever, and it's useful in mathematics, especially when we talk about natural logs. You usually have a base of e and principal and interest. Perhaps you remember the formula PERT. There's another place that you've seen e, were compound interest formulas. So the derivative of e to the x is e to the x, and a quick little proof of that I've written out for you by using the limit process I've gone through. Every time you see an x, replace it with x plus h, and you can see I've gone through, here was the goal, to eliminate the h's and then evaluate it at, as h goes to 0, of course there's no h left, so the derivative of e to the x is just e to the x. You're welcome to look at that proof, but if you can just memorize the derivative of e to the x is e to the x, I'll never ask you to prove it. So this one says write the equation of the tangent line. Here's the function, so let's take the derivative of that to find the slope, and the derivative of 2x is just 2. The derivative of negative 1/2 e to the x, well, this is a little bit helpful to use the constant rule. That negative 1/2 just pops out, just drags along, and the derivative of e to the x is e to the x. And of course, we want to evaluate at x equals 0. So we will go find the derivative at 0 by letting x be 0, and e to the 0 is 1, and 1/2 times 1 is just 1/2. 4 halves minus 1/2 is 3 halves. So hopefully in part A, we can see on the next slide that y is equal to, well, we've got a slope, at least at that point, of 3 halves x plus some b value. I would go back and let's plug in x and y and solve for b. So negative 1/2, well, this is nice because x is 0. That wipes that term out. And it looks like b is negative 1/2. So the equation should be y equals 3 halves x, and then minus the b term, and that's just part A. Just checking it before I move on to part B. Yay. All right, or was that part B too? What was it? Find the points on the graph at which the tangent line is horizontal. Well, horizontal means where this thing is set equal to 0. More precisely, where the derivative equals 0, because that would give us a slope of 0. So I'm going to set the derivative equal to 0 to find that horizontal line. So I'm going to subtract off a 2 from both sides. Let's multiply both sides by negative 1. Let's multiply both sides by negative 2, giving me 4 is equal to e to the x. And then to undo addition, we do subtraction. Undo multiplication, we do division. To undo an exponent, I'm going to natural log it. the natural log of e to the x and use the dump down property for my log and say x is equal to the natural log of 4. So I've got where the x value is, but it asked for the points. So I probably want to go find the y value as well. So I've got the natural log of 4. And to find the y value, I just go back to the function and plug in the natural log of 4. So the function is right up here, 2x minus e. Let's try that. 2x minus e to the, e to the x divided by 2 is the function. So if I plug in the ln of 4, I get 2 ln 4 minus e to the ln of 4. Here comes another log property, which you may or may not know, but e to the ln undoes each other, kind of like addition and subtraction, because they're inverses again. So that's just going to be 4 divided by 2 is a 2. So there's a 2 and there's a 2. I could even factor out a 2. You don't have to. Ln of 4 minus 1 is that y value. So a little bit of log properties there for you. And wanted to check. Looks like the author totally cheated and he just plugged in the natural log of 4 into the function and went decimal. So, but if I were to ask for the exact answer, I think he would do it like I did on the previous slide. So on the last problem, we were finding horizontal tangent lines, and that's when the tangent was equal to 0. This one says find the tangent and when the slope is 6. So I'll just set the derivative equal to 6. So let's go find the derivative of this function, which is 6x squared minus 30x plus 24, and set it equal to 6. Next, we'll factor out 6, leaving me with x squared minus 5x plus 3. And then depending on whether you want the exact answers or decimal approximations, you can take this. So this doesn't factor, so I'd have to do the quadratic formula to find the exact answers. B squared minus 4ac all over 2a. Or I can just go to my calculator and guess left, guess right, guess on, graph the thing, and go find the roots. So I think the author's done that for you here and here. So I'll leave that up for you to finish. Higher order derivatives say, well, we can take the second derivative. It could be denoted as this or this or this. The derivative of the derivative is the second derivative. And then similarly for just values of n. So higher order, find the third derivative. Well, the first derivative is 3 times 3. Decrease the exponent by 1. Second derivative would be the derivative of the derivative. So 18x. And then the third derivative would just be 18. If they ask for the fourth, I'd go to 0. So the first derivative here is 3 plus 2e to the t. The second derivative is the cons goes to 0, so 2e. And then the third derivative is also 2e to the t, and then you just keep going. And all good. The author has similar responses. So there's more practice. You don't know the product rule yet because we haven't done the next section. So you don't want to do the derivative of the first, write down the second, plus the derivative of the second, write down the first. That's in the next video. Besides, you want to simplify first. That's huge. Before you just grab the bull by the horns and start taking the derivative of this thing, think about how to simplify all of these things and then take the derivative. For example, for number 25, you can FOIL that thing out first, multiply it all out, and then take the derivative. And then for number 26, you distribute the r squared to every term, and then go back and distribute the 3 to every term, and multiply, stack, and add. And this one you FOIL out, and this one you can multiply too. So you don't always have to do the product rule, which we're going to learn in the next video. In fact, this slide is really important. because it's reminding you that we want to simplify these things before we have to do the product rule. Unless the directions specifically say use the product rule, then you can't simplify first. So you got to, but again, to simplify this one, I would change it to exponents. And I'm assuming you know how to do that. If not, you can shoot me an email. Let's see, you rewrite the base and add the exponents. Oh, that's interesting. And then you would take the derivative of this, which I think you can do. The derivative of x is just 1 minus 1/2 x to the negative 1/2. Oh, and you might want to throw the back, since they had radicals, let's go back to radical form, 2 over the square root of x. So work these out on the worksheet. If you haven't downloaded the worksheet, I would encourage you to. I've got worked out solutions here. Oh, good, we got that one right. And I've got a whole bunch of examples. So go through these, work through these, and if you have questions on how to get any of these answers, then shoot me some emails and I'll discuss that together with you. Good luck.